Okay.
I think it's working.
Bueno.
Check on YouTube.
Okay, well, es un gran placer de estar aquí, and thank you so much for hosting me. I'm really delighted to talk to this audience, and sorry again about the delays. So I wanted to talk about some of the science that I do. I consider the philosophy of my science to be interdisciplinary. I combine protoplanetary disk modeling about planet formation with data from meteorites. And I wanted to give you a taste of some of what I do there. And so I want to talk about the issue of whether planets form by planetesimal accretion or by pebble accretion. So let's see. All right. These are the two main paradigms for how planets might grow, and it's a question that applies both to solar system planets as well as exoplanets. Planetesimal accretion is basically the idea that planets grow by accreting asteroids. And the idea of pebble accretion is that they grow by accreting small, maybe even centimeter or smaller sized particles. And right now, astrophysics is at an impasse about which mechanism dominates, as I'll explain. But we can use geochemical and other information from meteoritics and planetary science to address this question. And I'll talk about volatiles and moderately volatile elements, as well as other species that are ingassed into magma oceans of planets as they're forming, as well as a little bit about hafnium tungsten dating and things like this. And hopefully at the end, I will be able to convince you that pebble accretion plays a role in the formation of the terrestrial planets, and I want to present some scenarios for how Earth, Moon, and Mars might have formed. What this means for evolution of protoplanetary disks and exoplanets. Oops. So first I'll share with you a piece of meteorite. I don't know, I love meteorites. So this is a piece of Allende, and it's a carbonaceous chondrite. And it's very much like this chondrite that you're seeing here, the scale bar. This would be about 1 millimeter size. So this is full of little things called chondrules that were individually melted while floating freely in the solar nebula in the protoplanetary disk. And I never get tired of talking about meteorites. But this is also probably what was in the solar nebula at the time asteroids were formed. And it's now understood that asteroids formed very quickly by scooping up millimeter-sized particles, those chondrules, into bodies that are 100 kilometers in size. And Morbidelli et al. Championed the idea that asteroids are born big. The size distribution indicates that you suddenly went from millimeter-sized things to 100-kilometer-sized things. And the mechanism for doing that was almost certainly the streaming instability, which is a mechanism by which particles floating through the solar nebula will tend to clump up. This is a face-down view of the disk where the sun is this way, and you're zooming in on a small region. And because of the motion of the solids through the gas, they tend to pile up. And very quickly, within a few orbits, when conditions are right, it's possible to form something as large as an asteroid from these clumps of material. And that's the start of how you make planetesimals. Planetesimals would be what I call these asteroid-sized things. But to get streaming instability to work, people have talked for a long time about, since the beginning of the model, about the particles being larger. But I think they're really the chondrule-sized things that make up asteroids, that make up that meteorite that you're seeing here. This is subsequent work doing numerical simulations of how effectively material can clump up and gravitationally contract into an asteroid based on two parameters. This one is the logarithmic scale. It's basically the size of the particle. And this is the concentration of the particles, the solids to gas ratio in the disk. And the dark blue denote combinations of those two parameters, particle size and particle concentration. that lead to clumping. And the first simulations showed that this size of particle, which corresponds roughly to 10 centimeters or a meter, was most effective in clumping up to form asteroids. And a lot of the first simulations of streaming instability focus on those sizes. But I think today we understand that even very small particles that are millimeter in size can clump up into asteroids and form them very quickly, provided the concentrations are high enough. And those concentrations are probably high enough due to turbulence. And turbulence can concentrate even millimeter size, actually especially millimeter sized particles, into zones where the solids to gas ratio is increased by factors of 50 or more in regions that are 100 million kilometers in size. So to me, this is pretty compelling, and this is how we make planetesimals, and that seems to be something that happens. But once something gets larger than a critical size that corresponds to the largest asteroid, it can also accrete those millimeter-sized chondrites directly through this process called Pebble Accretion. And this was also only discovered in the last 15 years or so. It's understood that if a body is in space and particles intersect it, and they will tend to go into, they'll tend to be gravitationally focused. And that can enhance the effective cross-section by factors of about 1,000 above what they would be if the particles just had to hit directly. But that's not enough to grow a planet the size of the Earth in a few million years, which is only the time that we have before the disk goes away. But in 2012, it was recognized that if this process happens in the presence of gas, that changes things, because particles that are gravitationally focused but miss the planet would be in hyperbolic orbit, and they would go very fast, but then they would escape the planet. But if there's gas, then the gas drag can slow down the particles enough that they don't escape the planet. And now, basically, any particle that intersects within a Hill radius of a body will eventually be accreted. And this increases the effective cross-section by a factor of 1,000,000 over the case of just direct capture. So that is actually fast enough that a planet can grow to Earth size within a few million years. But it does require that gas is present, and it requires that the body be at least as big as Ceres. But once you have a body that is about that mass, 10⁻³ Earth masses, then this is a similar graph. This is the size of the particle on this axis. And this is how effectively it is accreted. And small particles are very effectively accreted. So you can get Earth-sized bodies in a few million years by accreting millimeter-sized, chondrule-sized things. And the main question is, which of these two mechanisms, Earth accreting from asteroids or Earth accreting from pebbles, dominated? And there is a presumption that pebble accretion can't really work to form Earth and the terrestrial planets because of this issue. So one thing about particles that are in this size range, that are millimeter size to 10 centimeters in size, they drift, radially drift with respect to the gas, because they are trying to orbit the star at a Keplerian velocity, whereas the gas feels pressure support and is orbiting the star at a slightly slower speed. And because of that, particles are going to feel a headwind, and they will lose angular momentum and spiral into the star. And the drift speed with which they move in is given by this formula, and it has to do with the pressure gradient. And for particles that are millimeter size, they will tend to drift in at a rate comparable to 7 astronomical units per million years. So that is actually really high. And because they drift in with a pretty high rate, that means that there's actually a small efficiency with them being captured by a planet at any given radius. And so maybe only 1% of the particles crossing the Earth's feeding zone would actually be accreted by Earth. And therefore, if you were to make a planet from pebbles through the mechanism of pebble accretion, people said you would need very high pebble fluxes. You need about 100 Earth masses of pebbles to drift in past the Earth so that 1% of them could be captured. And that's very high, and there's a lot of reasons why we don't think that applied in our solar nebula. And so for these reasons, a lot of people have kind of dismissed the idea of pebble accretion. So in summary, right now, the impasse in astrophysics is, right now we know that planetesimal accretion must happen. We see the effects in meteorites. We see that streaming instability or a similar mechanism put together asteroid-sized things out of chondrites. And anyway, you cannot even start pebble accretion until you have some very large asteroids. And we know that planetesimals can accrete into Mars-sized bodies within a few million years. And there are these problems with the inefficiency of pebble accretion. On the other hand, those who study the bodies in the outer solar system know that they have cores that are 15 Earth masses. And it's impossible to imagine that growing by planetesimal accretion. So the cores of Jupiter, Saturn, Uranus, Neptune must have formed by pebble accretion. Maybe things were different there because they're beyond the snow line or something, but we definitely need pebble accretion for those. And we see exoplanets, they have thick hydrogen atmospheres sometimes, and therefore must have grown quickly enough before the gas dissipated in the disk. So pebble accretion is thought to have created those planets. And anyway, pebble accretion is a mechanism which seems inevitable, but again, maybe it requires special conditions to operate. So we'd really like to know, did the Earth, the Moon, and Mars form by pebble accretion or planetesimal accretion? Because right now, the modeling from first principles and the astronomical observations are equivocal. So let's look at the compositions of Earth, Moon, Mars. And the first thing I'll mention is that they are isotopically distinct. This was one of the major findings for meteoritics in the last 15 years, is that there are 2 flavors of isotopic reservoir in the solar nebula. You see this from many systems. This is excess of titanium-50 isotope and excess of chromium-54 isotope. And everything in the inner solar system plots in this part of the graph, and everything in the outer solar system plots in that part of the graph. And those are carbonaceous chondrites like the one you were just holding. And this is, these are called CC, therefore, because they're like carbonaceous chondrites. And this region is called NC, not carbonaceous chondrite. And it includes Earth, Moon, Mars, and a lot of other meteorites. And we see this same division in other isotopic systems like molybdenum. Things plot on one section or on a different section. So we know that Earth accreted almost entirely from material that is recognized as being in the inner solar system, and Mars as well. In fact, people who model what mix of known meteorite types might match the compositions and isotopic compositions of Mars and Earth would say Mars is about 100% this type of material, and Earth is 95% at least this type of material. So it's only accreting things from the inner disk. And that is the main reason why a large pebble flux through the inner disk cannot be the answer for forming Earth by pebble accretion, because If you have to bring in hundreds of Earth masses of material from the outer solar system, it would definitely be this CC type material, and that is just not what we see. So immediately, if you're going to have pebble accretion, you must explain why there are so many pebbles. Another thing we can look at are volatiles. These are species that vaporize at low temperatures, including water or carbon, nitrogen, or sulfur. And these are indicative of colder temperatures. And so carbonaceous chondrites have more of these volatile materials, and Earth has less, actually. So one thing we can do to figure out if Earth and Mars are forming from chondrites is to see if the mix of meteorite types that people have invoked for Mars and for Earth bring enough volatiles to explain the inventories that Earth and Mars have. Okay, so this actually comes from a book chapter that I led, and I have an extra copy of the book that I'd like to leave in the library here when we're done. And in this book chapter I led, that we looked at the mixes of chondrites that Earth is presumed to be. One mix is 71% enstatite H type chondrite, 24% ordinary chondrite of type H, and 5% this carbonaceous chondrite CV. And there are a few other mixes of known meteorite types that people have suggested for Earth. And similarly, different people have mentioned different mixes of meteorite types to explain Mars. And so what we can do is we can say, how much water do these meteorites have? How much carbon do those meteorites have? Nitrogen and sulfur. And if the Earth and if Mars were made of those, then these are how many Earth masses or Mars masses of those volatiles we expect them to have. And then we can compare to what the planets actually have, which is tricky because we know what's in Earth's mantle and crust, and we have a good idea of what it is in Mars's mantle and crust. But actually, most of these elements are in the cores of the planets. And so one has to model that part, and it gets uncertain. But nevertheless, people have estimated, and we reviewed here, how much total water, carbon, nitrogen, sulfur we think exists in these planets. And then we can compare to what they were predicted to have. So for Mars, it's really not possible to compare carbon and nitrogen because, again, we don't know how much is in the core. But its water and its sulfur abundances are pretty good matches to what meteorites would give them if it's the mix of meteorites that people have suggested for Mars. So Mars could be made of asteroidal material as represented by known meteorite types. Whereas Earth, the amount of water Earth has might be a good match, but Earth has way too little carbon, nitrogen, and sulfur compared to what meteorites would bring to it. So you cannot form Earth by taking known meteorite types and combining them in the ways that have been suggested, and you would have way too much carbon, nitrogen, sulfur. So that is a hint that Earth was not formed by planetesimal accretion. There's another chemical trend we can look at, moderately volatile elements, or MVEs. These are elements that would vaporize at temperatures of between 500 and 1,000 or 1,200 Kelvin. And when we look at the abundances of these elements in different meteorite types, we see this very interesting trend. So this is the ratio of an element like potassium relative to magnesium. And then that ratio of potassium to magnesium is divided by the ratio in Ci chondrites, which is a type of carbonaceous chondrite used for standardization because it probably resembles the sun. And so compared to the starting material in the solar system, all of these different meteorite types, these are CM, CBCR, different types of carbonaceous chondrites, they are all depleted in potassium. And the more volatile the species, the more easily it vaporizes, the more depleted these different meteorite types are. And so there's this very interesting trend, the moderately volatile element volatility trend. And it turns out Earth is these, and Earth is also depleted in the same pattern as these other meteorite types, but it is more depleted than any known meteorite type. So it's not possible to combine different meteorite types and get the Earth, because the Earth is more depleted than any of them in these species. So this has been interpreted by Connell Alexander and collaborators as meaning that the Earth might be composed not of the bulk chondrite meteorite types, but actually the chondrules, those little spherules of melt droplets within them, because the chondrules themselves have been heated and have lost volatiles. And it's almost as if the Earth accreted just from chondrules. And that's their interpretation. And we can do the same thing for Mars. There is a similar plot of the depletion of those moderately volatile elements in Mars. And it turns out Mars is also depleted, but not really, it's not more depleted than any meteorite type. It's about as depleted as CV chondrites. And it's an open question whether Mars is made up of that type of meteorite or other types of meteorites, but it's harder to say that Mars could not have formed from planetesimals. It could have, and that would match the moderately volatile element trends. Okay, another constraint we have is in-gassed species. So we know from some exoplanets that they have hydrogen atmospheres. Some rocky planets that are fairly larger than Earth have hydrogen atmospheres. And they must have accreted those atmospheres while their solar nebulas, their protoplanetary disks, had gas. And every planet probably goes through a stage where it's completely melted and has a magma ocean of melted rock on its surface. And it's possible for gases like the hydrogen or helium to dissolve into the magma ocean of those planets. And while we can't observe that in exoplanets, we do see the evidence of that for Earth. So Earth contains, Earth's mantle contains helium-3 and neon, which has 3 isotopes, but that are characteristic of a solar nebula gas. And from an isotopic standpoint, it's very clear that solar nebula gas dissolved into Earth's mantle. And there's something like 10 to the 14 moles of neon and helium in gas. And Earth's mantle also contains some isotopically very light hydrogen. So that's very low in deuterium hydrogen ratio, which we do not see in any meteorite types, but we do see in the sun and Jupiter's atmosphere. So solar nebula gas has very light hydrogen, and we see that that also exists in Earth's mantle. And some detailed modeling that I was involved with, we estimate something like 1 bar of, so 1 atmosphere of pressure of hydrogen had to be on top of the Earth's magma oceans, or the magma oceans of the planetary bodies that eventually made Earth. So one could make a model where you have 2 embryos of 0.3 Earth masses, each with atmospheres of about 1 bar of hydrogen, and then later they combine and form proto-Earth. As well, the moon has some very low D to H isotopically light hydrogen in it. And my collaborator, Kitty Robinson, measured this in Apollo 15 samples. And it's so isotopically light, it can't be anything but solar nebula gas, in-gassed into a magma ocean, but not into Earth, actually into the body that hit the Earth to make the moon, which we call Theia. And some detailed modeling there, we estimate something like the amount that it would require is 20 bars of hydrogen, which is consistent with Thea being actually 0.4 Earth masses in size. So that would require Thea to be 0.4 Earth masses while the nebula gas was present.
Excuse me.
Yes.
Wouldn't that same reaction produce water? Like if you have a magma ocean that's in contact with hydrogen, that would lead to water. Can that explain water's Earth without invoking any comet pollution or like delivery of water from external sources?
Right, yeah, so the hydrogen can react with silicates. It can produce water through that reaction. I think the numbers don't work out to make as much water as Earth has, but it is certainly a mechanism. I think Ed Young and others have looked into that as an important mechanism. Yeah, from an isotopic standpoint, it doesn't matter whether it reacts to form water later or not, but I'm trying to demonstrate that the hydrogen had to be there while you had a magma ocean. Yeah. And that requires it to be really fast. Oh yeah, I forgot to mention, yeah, there's Kepler 11f is the one that's thought to have a hydrogen atmosphere of about 15 bar. So pretty consistent numbers across the board. But you don't have very long to accrete hydrogen. This is work that I led in 2018, trying to map out where all of the different chondrite and other planetary types formed in the nebula using a sophisticated protoplanetary disk evolution model. And it's a function of place in the nebula and time. This is where everything formed. The reason I put this up is to demonstrate that nothing in the interior, few AU, seems to have formed after 2.5 million years. The solar system probably was a transition disk. Those who observe protoplanetary disks know that very often disks go through a stage where there is no or very little material inside about 3 AU after about 3 million years, and even as gas exists beyond that. So the solar system seems to have gone through that stage. And for terrestrial planets to accrete hydrogen and helium, they have to form within about 2.2 million years. And you have to have growth to 0.3, 0.4 Earth masses, as I was explaining. So that's very rapid. And also, it's not clear that the sizes are even attainable by planetesimal accretion. Models, I mean, there's a lot of parameters, but models tend to suggest the largest bodies that grow by asteroidal accretion in this time frame are maybe Mars size, and then it kind of stalls. So that's evidence that certainly Earth's embryos, the parts that made up proto-Earth and Thea, had to grow very rapidly, and that would require pebble accretion. So, right. And then finally, one other geochemical constraint is hafnium tungsten, which I feel obliged to just explain a little bit. Hafnium is a radioactive isotope, 182 hafnium. It decays to 182 tungsten with a half-life of 9 million years. And in a planet, hafnium will always go into rock, but tungsten will go into metal. So depending on when the core forms, you will either have the hafnium be in the mantle or its product will be in the core. So for example, if a core forms very early, it will take all of the tungsten that's there and put it into the core. And then the mantle will have 182 hafnium, which will then decay. And that will give any tungsten left in the mantle an excess of 182 tungsten if the core forms early. Whereas if the core forms very late, all of the hafnium can decay, and then the 182 tungsten that is made will just go back into the core at the end. And so you will not see an excess. And so meteoriticists measure this 182 tungsten excess, and there's a lot of math. I won't bother you with it. But the point is that Mars shows this excess of 182 tungsten that indicates that its core formed pretty early, and detailed modeling, like a phone per month, basically they concluded that Mars had to form within 3 million years. And again, that's consistent with formation by planetesimal accretion. People have used the fact that Earth has basically no or very little excess of 182 tungsten to argue that its formation must have taken a long time. And this has been a point made in favor of planetesimal accretion. And yeah, and there's a whole model. Wade and Wood's model is pretty standard in the field. That says that Earth grew by accreting asteroid-sized things over 100 million years, and that simply that could work. But it's also possible to just reset the whole thing, the isotopic system, during the giant impact. The core and mantle materials can mix, and then it's as if the core formed very late. So then it gets into the weeds about moderately siderophile elements, whether that's possible or not. I won't bother you with that either. But hafnium tungsten for Mars is consistent with it forming from planetesimals or pebble accretion just very rapidly. And Earth, it's got this low excess of 182 tungsten, but this actually doesn't distinguish between the models. It sort of demands that it be reset late. All right, so to summarize all of those geochemical constraints, Mars could have formed from chondrites. It's not really that depleted in volatiles or moderately volatile elements, but Earth could not. Earth is depleted in volatiles. It seems to have grown mostly from chondrules, and it had to grow these embryos that were very large very quickly. So I think we have to consider pebble accretion, and yet we know that pebble accretion is very inefficient if the pebbles are drifting, and they cannot come in from the outside of the disk because then they would look isotopically different. So how do we resolve this? And this is work that I've been doing. This is in prep with Takehiro Ueda. So let me remind you again that particles drift inward because they are trying to orbit the star at the Keplerian velocity, and you can balance the forces and find their velocity around the star. And the gas is also trying to orbit the star, but additionally feels this outward pressure gradient force if the pressure is high in near the sun and low far from the sun. And therefore particles feel a headwind that makes them slow down and lose angular momentum, and they will drift inward. Or if the pressure gradient is reversed, it's possible for them to move in the opposite direction, because the gas would be accelerated. They'd feel a tailwind and they'd spiral out. And basically particles always drift towards the pressure maximum. That's the key thing there. And there are formulas you can write to calculate this all. And I won't go through the math. But these are not the only things of interest. These are not the only determinants of how particles move. There's also the fact that the gas is moving and accreting in, and that will carry particles. And also, the motions of the gas are not uniform with height. Gas near the disk edges tends to move in, and yet at the midplane move out. And so it matters how big your particles are. If the particles are very big, they settle to the midplane, and because the gravity pulls them towards the midplane, in which case they get a movement out. But if they stay well mixed with the gas, then they might move in because the gas is moving in. So all of these things matter. Plus, and this is really important, if particles are concentrated at one radius and not so much at this radius, there will be a concentration gradient. And particles always diffuse from high concentration to low concentration. And all of these effects are equally important. So it's not just the case that radial drift is the only thing we should care about. And because of that, I think that people have overestimated the importance of radial drift. It's important, but it's also possible for particles to move out. As this explains, if particles are drifting in, they will tend to bunch up at this radius, but then they're going to want to diffuse against the concentration gradient outward. And you have to calculate all these things at once. So it turns out you can make a formula for the average velocity that particles would have. And basically this term here is a concentration gradient. You can always find a concentration gradient that would allow a steady state solution. And so this is what I was exploring in this work. So if you let the surface density go as r to the power of p, temperature goes as r to the q power, the turbulence in the disk scale with r to some power a, it's possible to calculate what that average velocity is. And it's going to depend on this parameter, which is through here is proportional to the particle size. So different particle sizes will have different steady state concentration gradients, but they'll all have a solution. So provided you have a disk model, you can calculate how particles are distributed in that disk. So the scenario that I'm investigating with Takahiro Ida is one that he's talked about before, where you have a disk that has different amounts of turbulence at different radii. Close to the star, where it's very hot, you can ionize the gas and trigger what's called the magnetorotational instability, or MRI. And so the gas is very turbulent. It falls onto the star very quickly. The surface density and the pressure of the gas is kind of low. And then far from the star, and by the way, we're talking about 0.15 AU or 0.4 AU. Beyond 0.4 AU, the gas is not ionized. It's less than 1,000 Kelvin, and it's got a very low amount of turbulence, and the gas doesn't move very quickly. And in between is a transition zone where it's going from being very turbulent and active to not active. And in this type of disk, it turns out this region is a pressure minimum, and this region is a pressure maximum. So particles tend to drift towards the pressure maximum, and some particles will still be found here, but not that many. Those that are here will be swept onto the star, along with the gas that's accreting onto the star. But for the most part, particles might stay in this region. And so I've been calculating steady state abundances. This is the concentration, a logarithmic scale of the concentration for a few different particle sizes as a function of radius. This would be where the MRI is active, and here it's not turbulent, and so on. Again, I can go through these numbers if you want, but the point is that you find that particles that are large, especially if they're large, centimeter size, are not very abundant at that inner edge. So they're not being lost to the star very effectively. And they are being trapped at that pressure maximum. And even millimeter-sized particles are not being lost that quickly. And this makes a big difference to the abundances of particles. Put another way, as a function of the size of the particle, this is the time scale in millions of years over which it's lost in an exponential sense. Particles that are millimeter size are the ones that are on this part of the plot. And it takes millions and millions of years for them to be lost. And so effectively, millimeter-sized particles are not being lost from the disk, thanks to this scenario, where you have a dead zone and an MRI active region. That sort of configuration allows pebbles to remain in the disk long enough to form asteroids. So I think by including all of these mechanisms, not just the radial drift, but the diffusion of particles and their settling to the midplane and the variation of gas velocity with height, putting all these things in at once, you find that pebbles are not really lost from the disk, and they can just stay in the inner disk for the millions of years you need to form these planetesimals. And that means that pebble accretion is made possible without invoking large pebble fluxes. And pebble accretion offers another thing that I think makes a nice match to the geochemical data, where you could have embryos that are accreting pebbles, but if these embryos are ever scattered by interactions with another planet onto an eccentric orbit, they're going to move supersonically with respect to the gas, and they'll develop a shock front in front of them. And this is something that I've worked on a lot. Most of my initial work in meteoritics was on explaining how it is those chondrules got melted in the first place. And this is the model that I favor. You have bow shocks around planetary embryos on eccentric orbits moving supersonically through the gas, and particles come in and are heated as they go through this, and they melt. And then they are either returned to the nebula, or they can be accreted onto the planets. So if you have these planetary embryos, I think this is how we make chondrules, but it's also going to be the case that these bodies will accrete chondrules. And in fact, while they're on eccentric orbits, they're going to accrete chondrules at a fast rate. And before I move on, I should mention, you can see the temperatures are very high. Any particles that go through this shock front are going to lose their volatiles. So yes, other simulations, Lou and Ormel, have shown that once you get a body on an eccentric orbit, like the eccentricities a few percent, it's going to accrete material via pebble accretion at an order of magnitude higher rate, or at least several factors higher rate. And it won't stay on an eccentric orbit forever. It takes a few 100,000 years for gas drag to damp it down. But while it's on an eccentric orbit, it's accreting mass at a much higher rate. And putting an embryo onto an eccentric orbit once allows it to increase its mass almost like double what it would have without that. And the material that it's accreting during that whole time is devolatilized and resembles chondrules. So I think that's a nice scenario for explaining the geochemical evidence.
Excuse me.
Yes.
So because, so I understand you devolatize the material, but isn't there a feedback region in which those volatiles are going to be kept around that core, and you could maintain it? I mean, I understand that most could try, but depending on your position of your embryo in the disk,
Right.
some of that volatile can be trapped inside all the time, and you will have a very volatile rich body, and others that the volatiles always escape.
Yeah, the volatiles are released here, and this gas is going to be swept back into the nebula. And yes, the rest of the nebula gas will see an increase in its volatiles, but and then those materials will condense onto micron-sized grains, become the matrix. But overall, that annulus is not affected. It's volatiles to refractory ratios and change. So yeah, but what would be accreted by the planet would be the solid particles that are devolatilized. Yeah. So I have other slides about the moon forming impact, but in the interest of time, I think I'll just skip them. I wasn't sure I wanted to go through them all, but suffice it to say that I've been working on scenarios for explaining the timing of different events in the formation of the moon, and timing when the Nice instability would have had to occur. The highlights are that I think the giant impact happened at around 50 million years, and that the moon took a very long time for its magma ocean to finally freeze, and maybe it froze a little bit and then was remelted actually through the tidal interaction. And that requires Earth's atmosphere, the Earth to be molten, and therefore it had to have a thick hydrogen atmosphere. but I won't belabor all those things. So to conclude, okay, in terms of using these geochemical constraints, we can look at Mars and we can see that its volatiles, its MVEs, and hafnium tungsten could be explained by either mechanism, and they're not really exclusive. You need planetesimals to form a Mars-sized, well, a large body before it can even start to accrete pebbles. And so depending on details, maybe Mars accreted some pebbles as well as planetesimals. But for Earth, you cannot form it just by planetesimal accretion in terms of the volatiles, the moderately volatile elements. The hafnium tungsten is a little more complicated, but it seems pretty clear that it would have been reset during the giant impact. And so it's not super diagnostic. You can't use hafnium tungsten to say the Earth had to form by planetesimals. But it is very consistent with forming by pebble accretion. It is as if Earth formed entirely from chondrules. And again, the ingassing of hydrogen and helium and neon into the Earth speaks to it growing very quickly, faster than planetesimal accretion could say. So stepping back and thinking about planet formation generally, Earth and Mars, we know they accreted local materials, and yet Earth looks like it formed from pebble accretion. Therefore, pebble accretion must occur without requiring large pebble fluxes, which are really often invoked in models of pebble accretion. And I think the reason we don't need to invoke them is simply that the pebbles weren't lost. If you have the right type of disk structure, they're not lost from the disk. A dead zone inner boundary is an effective way to keep them from being lost. And for people who model things like streaming instability, I think you have to look in the meteorites and recognize that what asteroids are full of are millimeter-sized chondrules. And you can argue about whether particles should grow to centimeter size if they grow until they reach the fragmentation barrier, for those in the know. But it seems pretty clear to me that they're chondrule size, and that's more consistent with growth being inhibited by the bouncing barrier. And Earth's embryos probably grew by pebble accretion, probably while they were on eccentric orbits. So scattering of embryos might be an important thing at a very early stage during the disk stage. And Mars never really was scattered onto an eccentric orbit, or else it would have grown from more devolatilized material. But I hope this gives a flavor for how I try to combine astrophysical modeling with meteoritic data. Astrophysical modeling from first principles has taught us a lot about streaming instability, pebble accretion, but it can't fully resolve all these issues. We need to incorporate meteoritic and planetary data to know how planets form. All right, thank you for your attention.
Hi, thank you for your talk. I was wondering, right now you were saying something about Mars not being so how all of this is affected by what was happening in the outer side of the disk? Like, does it have something that we should consider when we're talking about the formation of these planets?
Right. So going back to one thing we know is that Jupiter had to form very early to open a gap in the disk, or else the NC and the CC reservoirs would have mixed. But it seems very clear that it opened a gap so that there was a pressure low and then a pressure maximum, and so particles, bigger than millimeter size got trapped here. And that also means that we have a hard time understanding the sequence of events in the outer disk. But it's on the plus side easier to model how the planets must have formed here. But I do think, for example, chondrule formation, the actual timing of when those little things were melted, shows that at least the chondrules in our meteorite collections, they were mostly melted at 1.5 to 2 million years. They don't seem to be melted at 1 million years. So it's almost as if something increased the rate of melting. Probably the shocks were more frequent at around 1.5 million years. And I think that indicates that the planets, the embryos, were scattered more effectively after that date. And that would make sense if Jupiter, which was growing steadily during this time, reached about 100 Earth masses. At around that time, it could destabilize the orbits of those embryos. So there's definitely a lot of effects. Also, Jupiter is probably migrating at this time in the disk, and that can destabilize things here. So there is a lot of effects, but we're only beginning to understand them, I think.
Thank you so much for your talk. It's so interesting. I was wondering, how much do we think these processes would be affected by a different host star? Like if it was an M door? Sorry to ask the M door.
No, yeah, that's great.
Someone's got it different.
One hopes that these are more or less universal processes, but things will scale. So one thing that I will say this, like a Jupiter mass thing around a solar mass star at a few AU is not super common. So I think that Jupiter probably played an important role in all of this. It probably stopped the influx of pebbles. They got trapped in this pressure maximum beyond it. And we know from the meteoritics that this material did not mix into here. But what that means is that there wasn't a big pebble flux here. And there doesn't have to be to form a one Earth mass body. But in a disk without a Jupiter, that pebble flux could continue through, and then it makes it more sensible that you would form a super Earth. And so I think that having a Jupiter, for example, is a control on how large planets can get. So we ended up with smaller planets and without a Jupiter, like a super Earth. And then as you scale this to smaller masses of host star and different masses of disk, the same effects would happen, but you wouldn't need a Jupiter mass thing to form, to interrupt the flow of pebbles. And Earth mass thing might do that. What that means for planet formation, I'm not sure yet, but I think it would have a big effect on the size of the planets.
Thank you.
Yeah.
It's very interesting.
Yeah.
Thank you. Very interesting, and it's very nice to have this, which is sometimes very easy for us. So when you consider the formation of giant planets, how do you see Pebble Accretion as a mechanism that allows you to one size to the other? Is it still an important mechanism, or does Planetesimal accretion take over earlier on?
Yeah, my suspicion is that planetesimal accretion does not get you beyond a Mars size thing, and anything bigger than 0.1 Earth mass probably requires Pebble accretion. And Jupiter's core, just to open a gap in the disk, it needs to be 20 or 30 Earth masses. And it has to do that, according to the meteoritic data, very early. I mean, in less than 500,000 years, possibly 200,000 years. And it's impossible to imagine that by anything but Pebble accretion. In this scenario, I think it was aided by maybe existing at the snow line, where you can get a higher concentration of solids that can allow faster Pebble accretion. So I suspect, I speculate that Jupiter formed at around 4 or 5 AU at the snow line early on. That's where the snow line would be. And then it migrated in as it grew, and then finally stalled at around 3 AU. That's my speculation. And yeah, I'm not exactly sure if I answered your question, but these are the things I imagine.
think you did. So you are reinforcing even the idea that pebble accretion can be more mechanism, more dominant as mechanism for Jupiter than what we have evidence for Mars here.
Yeah.
We just don't have as direct evidence.
Right. It's just, but the meteorix is telling us that Jupiter has to form very early, surprisingly early. So yeah, it has to be Pebble accretion, I think.
Yeah, so I have a question about formation then of Neptune and Earth. So I understand Pebble accretion is more efficient beyond the snow line. There is higher viscosity, ice-rich material. But if you have a Jupiter and a Saturn and you have a pebble trip that goes always inwards, what is the mechanism really to form Uranus and Neptune? Like, is there any substructures that you like? Can you have something like a pressure bump at different locations in the disk that gets you enough material to form those bodies? Otherwise, you would just try to accrete everything at the snow line, right?
Right. Yeah, that is the way people look at it. From one standpoint, right now the hot topic in cosmochemistry is trying to determine if material was caught in the pressure bump beyond Saturn. So right now, I think there's a wide recognition that the pressure bump beyond Jupiter is where carbonaceous chondrites mostly form. And that seems to be established now. But there are variations within the carbonaceous chondrites, and it's thought that CI chondrites, Ryugu, Bennu, may be isotopically distinct, and possibly it suggests that they formed in the pressure bump beyond Saturn. But again, your question is, where does Saturn come from in the first place? And Uranus and Neptune, yeah. So I think the idea that there's a pebble flux in is true, but it's tempered by the idea that there's diffusion and this turbulent mixing, and you have to include those in the models, and I think they are not usually included, and they should be, and that'll affect the distribution of pebbles.
Can these mechanisms playing all at the same time lead to rings at certain locations that can increase efficiency for formation of planets at certain locations? Because from images of this, you see this type of rings. And I don't know if the nature of all mechanisms can lead to these formations where you pile up.
Yeah, so the ALMA images certainly show rings and gaps. Any place you do have a gap, beyond that you have a pressure bump, that's where particles will be concentrated, and that's a good place to make planets. It has been suggested that once you form Jupiter, it could, through the waves it launches, open gaps at different locations, usually interior, but I guess exterior, right? And then that may trigger the formation of the subsequent planets. That's an idea. I don't know.
Any more questions?
I have a question, but it's kind of like a weird question. In terms, like, there seems to be a difference, right, between Mars and Earth regarding how they were forming the pebbles of planets. Is there any link of any of this to why, for example, life happened on Earth?
Well, the biogenic elements that we've just, carbon, water, nitrogen, sulfur, yeah, these are going to be very different. And Mars is not as depleted in those biogenic elements as Earth is. Based on that, one might say Mars is more amenable to life than Earth, but it's not the only factor. So yeah, it's a big question.
We have a question. All right, let's thank our speaker again.
Who has my media?
I have it.
Okay.
And you have my computer.
And yes, okay, we'll trade.
We'll do the trade-off, and I'll stop being a computer.
I love meteorites because this is older than the Earth.
And where did you find it?
I bought this
Just
online.
outside.
Yeah.
You found it